All right, so 5.4, again, this idea of central limit theorem. Some interesting background on where this came from, so you can read through this introduction here on your own. We're going to jump into the actual notes itself, though. And so we're going to look at finding sampling distributions, verifying their properties, how to interpret the central limit theorem, and how to apply it to find the probability of a sample mean. So slightly different than what we've been doing in the past. Okay, so a couple key things here as we're looking at sampling distribution. So in this section, we study the relationship between a population mean. So remember, population is everyone involved, and random samples taken from that. And there's some slight variation in that. And so we deal with sampling distribution. So again, sampling distribution is this idea of probability distribution of a sample statistic that is formed when random samples of size n are repeatedly taken from a population. Population is going to be everyone. Sample is going to be smaller groups of that. And so within those, you can see in this nice picture here is, we get one sample, may have a different mean. We take a second sample, a third, and a fourth, and they could vary from low to high, and this one's going in that order, but this one could have been your first one, this one could have been the second one, that could have been 3, that could have been 4 and 5. Any order of those, just you're going to have 5 different samples. Means, because you have 5 different samples, we've talked about that as sampling variability. And so our sampling distribution consists of the values of our sample means. And so you can see that there is some overlap, and then some that had no overlap. And when you compare the two extremes, sample 1 and 5, there's a decent gap that falls between those. And so properties of sampling distribution of sample means has a couple key features. So notice it is mu and then x bar is equal to the population mean u. All right, so there's a couple of properties of sampling distribution of sample means. So we've used mu as our mean. Well, what we use here is mu x bar is how we would say this here, which refers to our Okay, so there are a couple of properties of sampling distribution and sample means. We have the mean of the sample means right there, and that's mu that we've been using, and then x bar is equal to the population mean mu. So those two things are equal. And the standard deviation of the sample means, all right, we have our sigma, and then x bar is equal to the population standard deviation, and that is by our standard deviation divided by the square root of the sample size n. All right, and so this is a key formula for us in this section. And so the standard deviation of the sampling distribution of the sample mean is called the standard error of the mean. Okay, key phrase there. Which brings us into our main topic where this all comes from. Central limit theorem forms the foundation for inferential branch of statistics, inferring based on data. Describes the relationship between our sampling distribution of sample means and the population that the samples are taken from. So it allows us to connect those two ideas. So let's take a look how this applies here a little bit. So the central limit theorem, if our sample sizes are n greater than 30, are drawn from any population with mean mu and standard deviation, then the sampling distribution of the sample mean approximates a normal distribution. And the greater the sample size, which we've seen when we've done simulations and we increase from 500 to 1,000 to 10,000, the better the approximation. Because in most cases, population distribution isn't going to be normally distributed. You're going to have some different groups that work in there. But then as we sample those means, we end up with something that is more distributed. And you can see that here as our n was increasing, our data become more approximately normally distributed. Then if the population itself is normally distributed, the sampling distribution of the sample means is normally distributed for any sample size n, right? And so if it's already normally distributed, then it doesn't matter the size of our n, where up here, right, our sample size had to be greater than 30. Down here, if it is already normally distributed, then our sample size n does not matter. And then we see the same characteristics that we've been used to. All right. And so, again, just some quick notes. In either case, the sampling distribution of the sample means has a mean equal to the population mean. So again, our sampling distribution, sampling means, is equal to the mean of our population. The thing that changes is the sampling distribution of sample means has a variance equal to 1 over n. And more importantly, for what we've seen a lot, is our standard deviation is divided by the square root of n. And remember, n is the number of samples. All right, so quick key of all these things, because I know it's a lot here. All right, so we have mu, which is our population. Mean. We have mu x bar, which is the mean of the sample means. We have standard deviation. we have population, standard deviation, and then the standard deviation of the sample means. Okay, so kind of follow each other. Mean of the sample means, standard deviation of the sample means. All right, so let's look at some problems here. We can apply this. And so we see a study analyzed the sleep habits of college students. The study found that the mean sleep time was 6.8 hours with a standard deviation of 1.4 hours. Random samples of 100 sleep times are drawn from this population, and the mean of each sample is determined. Find the mean and standard deviation of the sampling distributions of sample means, then sketch a graph of the sampling distribution. So the mean of the sampling distribution is equal to the population mean. So mu x bar, or our sampling mean, is equal to mu, which is equal to 6.8 hours. Okay, so pretty straightforward identifying that. Then 2, the standard error of the mean is equal to the population standard deviation divided by the square root of n. Okay, so identify our standard deviation, which was 1.4. Our n is 100. So then what we get is 1.4 divided by the square root of 100, or 1.4 divided by 10, which comes out to 0.14. And then 3, because the sample size is greater than 30, okay, so that's key. The sampling distribution can be approximated by a normal distribution with a mean of 6.8 hours and a standard deviation of 0.14 hour. So we're going to sketch that on top of our population distribution graph. Okay, so our mean was at 6.8. All right, and then we had standard deviation of 0.14. So it becomes super tight because 0.14, then we're at 608. And then 3 standard deviations gets us to 7.22. And then going the other way, gets us to 6.66, 6.52, and 6.38. So super small. That's why you saw super tight standard deviations, and that's why you really see this peak, because we still have to get 68% of our data here, and so you get something that looks way tighter than what we're normally used to.